Good day to all of you. In today's lecture, we're going to look into the topic called parallel algorithm models. So, right now, we are learning a lot of parallel algorithm techniques like parallel merge sort, parallel quick sort, which we would be learning. And then we've also seen what are the various matrices which can be used to evaluate a parallel algorithm. What is a task? What is a decomposition? What is mapping? What is a dependency graph, task dependency graph? And all these we have seen so far. Now, in this context, we are now going to look into a model, different types of model for parallel algorithm. And what do we call it? Which one do we call as a model? All right. For example, I have a very big task. I have divided my task into smaller portions, which I'm going to call it as a fragment, which I have decomposed. And each decomposition has something to do, an operation, which I call it as a task. All right, now that a larger picture has been divided into smaller tasks, the next activity is to assign these small tasks to a process which can perform the operation. So this is what you call it as mapping. All right. Now, when we say modeling, I have to think of what kind of a decomposition technique I can use, what kind of a mapping technique I can use, and what are the techniques or the strategies which I am employing to minimize my interaction. I would like to iterate here once again. What do you mean by the overhead involved with interaction? When I say there are 10 processes which are processing a task in parallel, as we have multiple times discussed this, there is certainly a need for one process to interact with the other process or to understand and to communicate with the other process in order to perform synchronization without any glitches or without any problem. All right, now in a parallel processing, if there are too many time, if there is too much of time which is invested or which is spent on interaction, then a parallel processing technique would perform as equivalent to a serial processing, because serial processing does everything on its own. Parallel processing does everything together in parallel, but it spends a lot of time in interacting with each other. So whenever we talk about models, we have to consider based on the three categories or three criteria. I can call it as a different type of a parallel model. So what are the three categories? One is selecting a decomposition technique. Number two is what technique I'm employing to map the tasks which I have decomposed to different processes. And the third one is to minimize my interaction. Only when I minimize my interaction, I can say, or I can be very sure that my parallel processing performs on par with any other high processing techniques. So there are 6 basic models which we will be looking in today's class. One is called as a data parallel model. Then we have task graph model, work pool model, and we have master slave model, and we have pipeline producer consumer model, and finally we have something called as the hybrid model. So we will be looking at all of these in this in the next slide. Okay, now we will move on to task data parallel model. All right. So out of all the models that we have seen so far, this data parallel model is the one which is the most simplified model. Now we will see how tasks are mapped. Okay, as we have been discussing earlier, we should talk about the minimization strategy, overhead minimization strategy, the mapping strategy, as well as how the decomposition can happen. All right. Now here we are talking about the mapping. There are 2 ways by which we can map. One is a static mapping, in the sense, well ahead of my computation, I will be dividing my process into smaller tasks, and even before the computation could be started, the processor can be identified for each of the tasks and it can be allocated those many processes. This is what we call it as static. But there are certain, definitely not all tasks can be done or can be mapped at the static level, because during execution, there may be a need for me to divide my task into further smaller tasks. And at that time, I have to only dynamically find out those processes which are free and allocate the task to those processes. But in this technique, data parallel model technique, most of the tasks are mapped to a processor only on a static or sometimes on a semi-static basis. So here, what kind of operations happen? The key point here is, if I have certain operations where the operations are very much similar, but it's just that they operate on different data, then I can go for parallel model. I will just tell you one simple example. Let us say that my only task is to add 10 numbers. So what is common here? The same number of tasks, that is adding 10 numbers, is the task which is common to all the processes. But what is different on all the, say for example, I'm employing some n processes. Not all n is going to add the same 10 numbers. 10 numbers are going to be added, but not the same 10 numbers. So what is different here? The data upon which these tasks are performed on are going to be different. So this type of parallelism leads to something called as data parallelism. Say, for example, I want to find out the aggregate of all the students in my college by adding all the semester marks. All right, so I would be adding, if it's a UG program, I would be adding all the 6 semester marks. If it is a PG program, I would be adding all the 4 semester marks. So here, what is common? Adding all the marks and getting the aggregate is common. But am I going to supply the same data? No. Each student, say I have 4,000 students, each student is going to have a different value. So here what happens? I am able to employ different processes to perform the same operation, but on different data. So what is the result here? I have achieved data parallelism because everything is going to happen in a parallel fashion. All right. Now, all tasks perform similar computation, the decomposition, data partitioning, because I'm going to uniformly partition everything. I'm not bothered because the performance is going to be the same. The load balancing is going to be the same. I'm going to add, and perform the calculation like average or aggregate or whatever. But the data on which I'm operating on is going to be different. So it ensures that there is a certain level of load balancing. Load balancing here, I mean, if I have 10 processes, there should be a fair share of data, fair share of load among all the 10 processes. There can be instances based on the problem where one process might be overloaded with a lot of tasks, whereas the other might be allotted a lesser task. But in data parallel model, we don't have such issue. All right, we will move on. The next one is about task graph model. Okay, now before that, we will see the implementation. So when we are talking about the data parallel model, there are 2 ways in which it can be implemented. One is a shared access space where the memory is shared. The other one is message passing, where a dedicated memory is allocated to each of the process, but they communicate by means of message processing. So each of this has their own advantage. If it is a shared access space, then there should be a better control. And if it is a message passing technique of implementation, then there is not much effort required from the programming perception or programming's point of view. All right. Now, what are we going to do with minimizing the interaction overheads? We can do something called as the locality preserving decomposition. In the sense, I'm going to decompose and I'm going to ensure that all the tasks are available within the same space. It is not going to be distributed, or it is not going to be moving far away from what we actually have. Okay, this is what you call it as locality preserving decomposition. And there is another nice way of minimizing the overhead: overlapping computation and interaction. Instead of me allocating a separate time for interaction and separate time for computation, I can ensure that these two happen parallelly so that I can bring down the time that is involved in interaction. So here, another advantage is, as the number of size of the problem increases, my degree of parallelism is also going to increase. Let me just tell you quote the same example of calculating the aggregate of 4,000 students. If I'm going to calculate the aggregate of 5,000 students, where the size of my problem is increasing, then my degree of parallelism will also increase, because I'm going to employ some 5,000 processors to do the computation. So this is as simple as that. The next one is the task graph model. So as we have already discussed, we have something called as a task dependency graph, which is a acyclic directional graph, where it tells you which task is dependent on which other task. Accordingly, the parallelism can be implemented. So this is whenever there is a lot of interrelationship that is existing among the tasks, then definitely this task graph model is going to help in lot of understanding of which task should be performed first and which can be performed after which task, and details like that. And it is a means of promoting locality-based decomposition, and also it is a means of reducing the interaction cost, because I'm going to keep whichever is going to have a better relationship with each other will be closely associated, so that the interaction time can be lessened. So when there is a huge amount of data to be performed, and when you have a lesser computational speed or lesser computational provision for you to operate, in that case, this task graph model is going to be really helpful. So what is the technique that is used for reducing the interaction? So reducing the volume and the frequency of interaction can be done by, as we have seen in the other example, the same way, promoting locality while mapping the task based on the interaction. And you can also, you can try to overlap your computation as well as your interaction, thereby bringing down the status or bringing down the time for doing the task. All right, the third model is called as the work pool model. So far we were talking about what is static mapping, semi-static mapping, and other things. But when you have a lot of dynamic data for processing, then this is the best model for you to work with. Work pool model, it does a lot of dynamic mapping of the decomposed tasks onto the processes, and it can happen either in a centralized way or in a decentralized way. So whatever be the task, whether it is centralized or decentralized, I should understand which process is given which task. So how do I make sure that I have a mapping of all those? Where do I have this mapping information stored? So I will have pointers which can be stored in a physically shared list, or it can be a priority queue, or I can use any of these data structures like hash table or tree or whatever, which can give me an information of task number 1 is in which process, task number 2 is in which process. That kind of a mapping information can be stored in such data structures. And so the processes may generate work, or it can keep on adding a lot of work. Since it's a dynamic based model, whatever be it, I will keep on extending my data structure by adding a pointer to the assigned task there. So the preferred one would be for a dynamic generation, a decentralized one. And also there is another important mechanism that is required here. If a task is divided into multiple things, it should be readily available for other tasks to know whether the task has been completed or not. Say, for example, I am adding 10 numbers and I'm going to give you a final value. So this I have divided into 5 processes with 2 numbers each. Now, process 1 would have finished adding 2 numbers. Process 2 would have finished adding 2 numbers. Same way, 5 processes. But the interaction should be among these 5 processes to know at what point the program or the processing could be stopped. The termination point has to be understood by the processes. Only then it can carry out with the next process of another task. All right, so for this, it employs a termination detection algorithm, which can detect and tell you, yes, this process is over, this task processing is over, now you can move on to the next task. Kind of an information would be provided by this termination detection algorithm. The next model, the master-slave model, as the name tells you everything, there is a master, there is a slave. The tasks can be decomposed by the master, which can be allocated to the number of slaves which are present under those masters. So the manager, more like a client server or a master slave or a manager worker model. As we can see, one or more master processes generate work and allocate it to the worker process. So in further, what can be done? If the manager is aware what task has to be done, it can be done well in advance before the execution. Or sometimes if there is a lot of dynamic data involved, then it can be assigning the process to different, the tasks can be assigned to different processes at a randomly picked up fashion. But here it is very important to ensure that there is a proper load balancing which is maintained. Not one processor should not be overloaded with more tasks where the other is not given that many tasks. Got it? So this can be done in two ways. One is I can do it in phases, or I can just make sure that I complete everything before I can start off with the next task. That is how it can be operational. So the manager worker model can be generalized to a hierarchical multi-level manager worker model in which the top level manager feeds larger chunks of tasks to the second level and it keeps on growing. Okay, I will just tell you one simple example. Let us take the scenario of a college. You have principal, then you have the vice principal, then we have the heads of the department and the staff, and finally students. So if any communication to the students have to go, it doesn't come directly from the principal to the students. It comes via the hierarchy. Same way, the top level master will allocate the job to the second level master, who is actually the slave of the first level. And these second level masters will again further divide the task into third level. And depending on the complexity and the amount of work that has to be divided, based on that, the level of this master slave model can also be increased. The next one is the pipeline, or sometimes we also call it as the producer consumer model. So a pipeline, I think we've already seen multiple times what is the pipeline. Like before a task can be completed, the second task can be the readiness and the preparedness for the second task can be started, so that without much delay, the second task can be started even before the first one completes its execution. So if again we were talking about granularity, fine grained, coarsely grained, and things like that. I hope you remember. When you have a larger granular task, then this is going to take a long time, because for the first task to understand that the second task can happen, by the time a lot of time would have already been spent in processing the data. So it is the other way. If the tasks are fine-grained, then it becomes very simple. The processing and the execution can be done at much faster pace. Okay, let me just read it out for you. The larger the granularity, the longer it takes to fill up the pipeline. And for the trigger produced by the first process in the chain to propagate to the last process, because it's highly granular. By the time it reaches the last process, we would have wasted a lot of time waiting. Now, if it is going to be too fine, then though it will definitely increase, but it will require a lot of interaction, leading to a lot of interaction overhead. That is again the problem. So there needs to be a perfect balance of the granularity. It should not be neither too fine nor too coarse for the execution to happen in a seamless way. The last one is the hybrid model. As we all know, that can be combination. I can put this master slave and pipeline together, or I can have data parallelism along with say worker workflow, or this task dependency graph model. There can be multiple combinations of this. A hybrid model may be composed either of multiple models applied hierarchically or multiple models applied sequentially, depending on the requirement. So in today's class, we've seen 6 different models. We will just quickly see what these are. We have data parallel model, we have task graph model, work pool model, master slave model, pipeline, which is always called as the producer consumer model, and finally we have hybrid model. Thank you, all of you.